Today, let's talk about Kirchhoff's laws. Kirchhoff's laws were given by Gustav Robert Kirchhoff, who gave two laws which are very fundamental to circuital analysis. So, the first law is called current rule or junction rule, and the second law is called voltage rule or loop rule. So, the first law, the current rule, is derived from the law of conservation of charge. It basically states that if I have an electric circuit and there's a particular junction in it where the current can flow either in or out of the junction, I label these points. I label the junction O outside as A, B, C, D and E. So if current flows into the junction from A, B and C and out of the junction from D and E, what the junction law states that the current moving into the junction AO and BO and CO is equal to the current going out of the junction DO plus EO. And if you ask why it's coming from the law of conservation of charge, well, that's pretty obvious from here. Current, after all, is the time derivative of the flow. Current basically is just the flow of charge. So the change in charge flowing through AO with respect to time and so on for the entirety of the LHS equals the change flowing through the RHS. So if I just multiply both sides by dt, that would cancel that. And now if I integrate it, I would get QAO plus QBO plus QCO equals QDO plus QEO. This is a quick and dirty algebraic proof, but if you want a more intuitive proof of why the current law is true, I would like to enlist the help of the pipeline analogy, which is what we apply to a lot of electric circuits. So let's say I have a pipe like that and another pipe coming in like that, another pipe over there, and then we have this connector connecting all of these pipes. And then this connector frees itself out again over there, and the outgoing pipes. If I take in water, let's say I push in 5 liters of water here, I pour only 5 liters of water into this, I pour 2 liters of water into this, and I pour 3 liters of water into this. At the end, the sum of the water coming through both of these has to be 10 liters because I poured in 10 liters of water. So 10 liters of water will have to come out. So it could be in any particular combination. It could be 4 and 6, could be 3 and 7, or it could be 5 and 5, or it could even be 10 and 0 if one of them is in a particular awkward angle. But the current law basically states that the sum of charges or the amount of watt which I'm pouring in to the junction is equal to the sum of charges or the sum of currents or the flow of water going out of the junction. So that's the Kirchhoff's current law. Now let's see what the voltage law is. The voltage law follows from the law of conservation of energy. Now the voltage law can also be followed with the pipe analogy, but I think I'll first tell the statement. The statement is that in an electric circuit, if a closed loop exists such as this one, and I have all of electric elements over here, an inductor, a capacitor and a resistor and so on. So if I have a closed loop in one particular electric circuit, the sum of the potential differences while traversing across the entire closed loop would be 0. Now what does that exactly mean? I'll show you with the pipe analogy, the water analogy. Now let's say I have a weird pipe like this. Now when I fill in water into this pipe, Let me draw that reference line over here, so somewhere around like this level. So when I fill in water into this pipe, the water fills in such a way that at the end of the filling, the water goes all the way across the pipe, and at the end of the filling, it reaches that exact same height, which on both of these ends. Why is that so? The potential energy at this particular height would be the same, and the heights, this height h and this height h, means both the water columns would exert the exact same amount of pressure throughout this pipe, this weird pipe over here. So the potential has to be same, and from energy to potential energy is but a step. So potential is given by work done per unit charge, that is electric potential. So work done, or rather the change in work done, equals the change in energy. From the work energy theorem, I can equate this to the charge multiplied by the voltage, or rather the charge multiplied by the change in voltage. So delta E should be 0 because energy is conserved. So which Q can't be 0 because the charge flowing through a circuit has some value, it's not 0. So delta V must be 0. So which is what Kirchhoff's voltage law states. The sum of the potential differences, the sum of delta V's, that is the sigma of delta V's rather, as you traverse this entire closed loop across the circuit, the sum of the delta V's equals 0. What the current law states in a different way is the sum of delta I's at a junction equals 0. Okay, cool. Now I know these laws. What do I make of them? How do I use them? There's one question which you probably have right now. So how do I use these? Well, Kirchhoff's laws problem are generally used to find out the current in all of the arms of the circuits, and the process is called solving the circuit or circuital analysis. So we'll follow some basic steps for this. Step 0, the initial step, if it's not already done, would be to label everything in the circuit. So here I label all of the points as A, B, C, D, E and F. And over here if you notice, B and E will be junctions. B and E will be the points about which we have to apply Kirchhoff's current rule. Next I'll label the batteries of the cells. I'll give them EMFs E1, E2 and E3, and I'll give the resistances R1, R2, R3 and R4. And the next step would be to, or rather this is the first step, it would be to assume current directions. What this means is that now I have no clue which way the current, I don't know what the current is, and that essentially means I don't know which way the current is flowing either. So because the EMF seems to be going that side, I'll assume that the current flow is along this way for the loop, or rather the arm EFAB, and I'll give that a name as well. I'll call it I1, and I'll also make a guess that the current splits over here into I2 and I3 over here. So from this we can directly now immediately apply Kirchhoff's current law, saying I1 equals I2 plus I3, and the same I3 would flow over here, and well, it moves against the EMF, but that's not a problem. So and the I2 and the I3 would recombine to form I1 over here. So from the junction B and E, and by use of Kirchhoff's current law, we can say that I1 equals I2 plus I3. So this is the first equation. The next equation, we'll need the loops for that. We'll apply Kirchhoff's voltage law. So I'll take the loop ABEF. In the loop ABEF, I'll start from point A. I have to go clockwise from point A and come back to point A. So here I'll measure the potential drops I1 R1 and E1, I2 R2 and I1 R4. So these are the potential drops across the loop, and I've gone in a clockwise direction. So this is 0, but then you notice I haven't filled any of these signs over here. To fill in the signs, we'll need to make use of the Kirchhoff trick, I would like to call it, the Kirchhoff voltage trick. So from my experience in solving Kirchhoff's law problems, I have made this tiny table over here. So the rule is whenever you're moving along an EMF, now I've been counting like that because I'm going clockwise, I move like that along the EMF. So if I move along the EMF, it is positive. If I ever move opposite the EMF or against the EMF, I take it as negative. Over here for E1, I'm moving along the EMF. So I take that as a positive. For the resistors though, there's a different rule. For the resistors, if I move along the direction of the current, that is the direction of current I've assumed. Now I've assumed I want to be in that direction and I'm moving along that direction. So I take that as a negative. And if I move opposite the direction of current, I take that as a positive. Over here, no. If I move in a clockwise direction for this loop as well, I'll have to take I2R2 as positive because I'm moving opposite the current. So let's fill up the remaining of ABEF. I1R1, yeah, moving along the current, so that's negative. I2R2 along the current, negative. I1R4 along the current, negative. Now let's take another loop. We've got one equation for I1, I2 and I3, another equation which has only I1 and I2. If I find the third equation, I would be able to solve it. I'll take this loop, B, C, D, E. B, C, D and E. So in the loop B, C, D, E, I'll start from B. I have an E2, I have I3, R3, and I have E3, and I have I2, R2, and this equals 0. E2 moving along the EMF, so it's positive. I3, R3 along the current, negative. E3 opposite the EMF, so this is a negative. And I2, R2 again moving opposite the current, so this will be positive. Now I have three equations for I1, I2 and I3. I1, I2, well okay, either way I have three equations. There's one more loop hidden in the circuit, and that is the loop, the outer loop, ACDF. Well, this loop isn't actually necessary, so ACDF, I'll just write that down anyway. So again, we start at A and we have to end at A. I1, R1, and then E1, and then E2, I3, R3, and E3, and then I1, R4. This equals 0. I1, R1 along the current, so that's negative, along the EMF positive, along the EMF positive, along the current negative, opposite the EMF positive, I1, R4 along the current negative. So this is another equation. We won't need this unless there's one more unknown in the question where we'll need this. Step 2 would be to write loop equations. And now that we have our loop equations ready, we can go to the next step, which is solving. So the third step is to solve. Well, we'll write these equations in a better manner. I1 minus I2 minus I3 equals 0. And then, well, there are two I1s over here, so I1 into minus R1 minus R4 plus I2 into minus R2 equals minus E1. Well, I could just multiply a minus sign everywhere, that make things so much easier. So this is the second equation, and the third equation, well, there's no I1. There is an I2 though, so I2 R2 plus I3 into minus R3 equals E3 minus E2. And now I could use any method of solving a linear equation, three linear equations in three variables. I personally prefer the matrix form because that's really quick and simple. So if you just apply the matrix form, using the matrix inversion, we can solve for I1, I2 and I3. I'll show you an example in the next video.